I'm going to give a presentation on dialogue over context and structured knowledge using a neural network model with external memories. Recurrent neural networks (RNNs) can capture the long-range dependencies of sequential data and therefore are capable of simulating arbitrary procedures if properly wired. However, RNNs are limited in their ability, for example, represent data structures such as graphs and trees, use variables, and handle representations over long sequences. To improve the performance of standard neural networks, Grace proposed a neural network model with an addressable external memory called differentiable neural computer. DNC solved various tasks, for instance, shortest path tasks of a route map. It represents data structures and question answering with premises. Input sequences were written to the memory, and necessary information to infer the answer was read from the memory, so it represents variables. And DNC is also able to learn long sequences by the dynamic memory access mechanism. So we found that DNC can handle context information, but how to integrate structured knowledge into DNC remains a challenging research question. So we extend single memory unit DNC models to a multiple memory architecture that leverages both contextual and structured knowledge information. We add an extra memory unit that encodes knowledge from knowledge bases. In contrast with RNNs, the memory augmentation of DNC allows an explicit storage and manipulation of complex data structures over a long time scale. I briefly explain the differentiable neural computer DNC. DNC is a neural network coupled to an external memory matrix. DNC uses attention mechanisms to define weightings over n locations of the memory matrix M that represent which location should be mainly read or written. For the read operation, the read vector R is computed as a weight sum over the memory locations by applying a read weighting WR over memory. And for the write operation, the memory M is modified by using a write weighting WW to first erase with an erase vector E, then add a write vector. Recently, variations of the DNC model have been proposed, such as the robust and scalable DNC. This is extended to focus on QA tasks. I skip here this time. And DNC DMS tackled problems of vanilla DNC and improved the model. I skip here too. As our proposed method, we expand three models, DNC, RS, DNC, and DNC DMS, by adding an extra memory architecture to store structured knowledge, like this. The differences from the original DNC models are to introduce the knowledge memory and add the operation for it. I'll show the procedures at every time step t. First, the controller RNN receives an input vector x, a set of R read vectors R from the context memory matrix at the previous time step, and a set of R read vectors Rk from the knowledge memory matrix at the previous time step. It then emits an hidden vector ht. Second, by linear transformation of ht, an output vector epsilon t and interface vector psi t that parameterized the context memory interactions at the current time step and an interface vector zt for the knowledge memory are obtained. The W terms denote learnable weight matrices. Third, the write operation to the context memory is performed using xit and its state is uploaded. The write operation to the knowledge memory is not performed. Finally, the output vector yt is calculated by adding epsilon t to a vector obtained by multiplying the concatenation of the current read vectors rc from the context memory and wc and a vector obtained by multiplying the concatenation of the current read vectors rk from the knowledge memory and wk, like this. The read vectors rc and rk are appended to the controller input at the next time step. The read and write operations to two memories are performed by repeating these procedures. Next, I'll explain how to build knowledge memory. We build a knowledge memory unit with a knowledge base, KB. Packs in the KB have a resource description framework, RDF triple structure, subject of relation object. For example, information such as Washington, D.C. is the capital of the U.S. is expressed like this. We apply the original DNC model, which has a single memory, to learn KB facts by giving the model all three components of a triple and any two of a triple, and then making the model learn to return the other of a triple. For instance, when inputs for the model are the U.S. capital, Washington, D.C., the U.S. capital, the output is Washington, D.C. The model was trained using all triples of the KB and produced a memory unit which stores the whole KB. We use this pre-trained memory unit as the knowledge memory unit in our proposed models. We trained the DNC model using memory dimensions of 512 times 128, because the results of our proposed models were better than when we also trained using memory dimensions of 256 times 64, which were the same as context memory dimensions in our proposed method. Whereas the context memory just stores its dialog content in the dataset, the knowledge memory stores the whole content of the KB, and thus it is reasonable that the knowledge memory needs to be larger than the context memory. And we evaluate the model with the accuracy and use trans-C for KB's word embeddings. The hyperparameters of our models are mainly based on the original DNC paper. We run every model 3 times under different random initializations and report the averaged results. We evaluate our approach on two Dialog datasets, the 6 Dialog baby task and the movie Dialog dataset. Both datasets require context comprehension and knowledge background and provide dialog data on a specific domain and audio triple data to answer questions in the dialog. The 6 Dialog baby tasks are a set of 6 dialog tasks within the goal-oriented context of restaurant reservation. Among them, we focus on task 5, which combines tasks 1 to 4 to generate full dialogues. Training, validation, test, and auto vocabulary test sets hold 1,000 examples respectively. The KV contains 8,400 facts in the restaurant domain. I present the mean per response accuracy of 3 different runs for all models. DNC is the original DNC model. Alice DNC refers to the robust and scalable DNC model. DNC-MD is a variant of DNC-DMS. Models with plus KM notation are proposed models with the added knowledge memory unit. DNC plus KM outperformed the original DNC on both who dialogues and auto-vocabulary tasks. Table below shows the result in detail separating tasks that can be answered without KV facts and tasks that require KV facts to answer questions. So DNC and DNC plus KM were the same on the without KV facts task, 99.99%. There was a significant improvement of about 14% on the with KV facts task. Alice DNC plus KM achieves the best performance overall and also improves the results on the with KV facts task by approximately 20%. Regarding DNC-DMS models, the scores of DNC-DMS plus KM were lower than the ones of DNC-DMS. We also conducted experiments on DNC-MD models, since DNC-MD suits better for QA tasks than DNC-DMS, and we found that the performance of the DNC-MD plus KM model was higher than DNC-MD. We hypothesize this is due to the nature of the knowledge memory, which does not use the temporal memory linkage. The order of the KV triples when building knowledge memory and the order of the words in the dialogue are irrelevant, so sharpness enhancement does not work well. Focusing on the Alice DNC plus KM model, we visualize the result of read or write attention weights on memories at every time step to investigate what the model wrote to memories and what it read from memories. This is a successful example where the outputs of the model are all correct. This figure shows write attention weights to the context memory on a successful example. The horizontal axis represents locations in the context memory and the vertical axis represents inputs of data or users' utterances and outputs of the model at every time step. There are strong attentions on KV words such as Paris and Indian, and it is interesting that there are also attentions on words used to change the conditions of a restaurant such as actually and instead. This represents read attention weights from the context memory. The slot where Indian was written to has an attention where when the model outputs restaurant information. The correct answer is an Indian restaurant, so read information of Indian is thought to be useful. This shows read attention weights from the knowledge memory. There are attentions before the model answers restaurant information, and distinctive features are not found compared to the context memory. Considering the visual write results, the contributions of the knowledge memory appear blurry. It might give the model some information about when to answer KV entities. However, the performance of Alice DNC improves by adding the knowledge memory architecture, so it's our future work to investigate the knowledge memory behavior in more detail. I'll skip This is conclusion. Thanks for listening.